This video is about three antiderivatives that yield inverse trigonometric functions. They're the last three rules on our sheet, the ones that we haven't gone over yet. So we're going to verify these using our derivatives of the arcsine, arctangent, and arcsecant functions, those derivative rules that we derived earlier this semester. And then we will actually apply those to solve some problems. We're going to find some antiderivatives. Now you'll see when you're evaluating antiderivatives that tend to involve these inverse trig antiderivative rules that we're about to introduce. Often we have to separate the numerator in order to evaluate the antiderivative, or use u substitution or complete the square. So we won't just be looking at three rules, we'll be seeing how those rules extend when we add these other techniques that we've studied, separating the numerator and u substitution, and then we'll add this one new technique of completing the square that often yields an inverse trig function as its antiderivative. So let's just state our rules. Remember this, earlier this semester we used implicit differentiation to derive the formula for arcsine of x. The derivative of arcsine of x turned out to be 1 over 1 minus x squared. The derivative for arccosine of x happens to be just like it, except it's multiplied by -1. The derivative of arctangent of x, we derived that earlier this semester, and we found that it was 1 over 1 plus x squared. And then when we derived the arccotangent derivative, we found it was exactly the same, but multiplied by -1. Then we looked at arcsecant of x, and that turned out to be a little different. We had 1 over the absolute value of x times the square root of x squared minus 1. And arccosecant was exactly the same. Its derivative was exactly the same, but it was multiplied by -1. So even though it looks like we have 6 rules here, we really only have 3 rules. They just sort of come in pairs. Arcsine and arccosine look like this. The cofunction gets the negative derivative. Arctangent and arccotangent look like this. The cofunction gets the negative derivative. And arcsecant and arccosecant look like this. The cofunction gets the negative derivative as well. So when we do our antiderivative rules, we don't really have 6 versions of these. We don't go from here to here, here to here, here to here, because these differ by a constant. These differ by a constant, and these differ by a constant. These 6 rules here turn into 3 rules for antiderivatives. So here they are. It turns out that the antiderivative of 1 over a squared minus x squared is arcsine of x over a. And we will prove that using this derivative rule for arcsine in just a little bit. Notice that that's a 1. We take the derivative, and over here we've got an a squared and we've got an x over a. So it's a little different, but it turns out if I take the derivative of this using the chain rule, I get this. Arctangent, it had a derivative of 1 over 1 plus x squared. So if I see something like this, it turns out that always gives me an arctangent as well. Turns out you get 1 over a times arctangent of x over a plus c. A is a positive constant. And then these 2 rules in reverse become this. We've got the antiderivative of 1 over x times the square root of x squared minus a squared. And that ends up being 1 over a times arcsecant. And this is the only one that's a little strange. There were absolute values, excuse me, on this side. So there will be an absolute value over here as well. So we've got the absolute value of x over a over there plus c. So these are our new rules. Notice the arc sine has an a squared minus x squared under a radical. The constant is first, and the variable that you're anti-differentiating with respect to, that's second. The arc secant has it the other way around. Let's verify these using derivative rules. So let's take the derivative of this side and prove it's equal to this side for each one of these. So I'm taking the derivative with respect to x of arc sine of x over a plus c. Well, that requires the chain rule because I don't just have an x inside, I've got an x over a inside. Well, according to our derivative rules for arc sine, the derivative of arc sine is 1 over the square root of 1 minus my inside function squared. So I replace x with x over a. And then I multiply by the derivative of the inside by the chain rule. And then the derivative of a constant c is just 0. Now this is a constant, it's 1 over a times x. So you're taking the derivative of a constant 1 over a times x. The derivative of a constant times x is just the constant, that's 1 over a. And the derivative of c is 0. So we end up with this. If I've got a fraction and it's being squared, I can square the numerator and square the denominator separately. And then I've got a 1 over a out here. Well, I can simplify this. I can bring that under the radical as long as I write it this way. I need to square it, and the square root of a squared is going to be equal to a, so I haven't changed the value of anything. But now that I've got a radical times a radical, I can use this rule to simplify that. If you've got the square root of a times the square root of b, turns out it's just the square root of a times b. So you can multiply the numbers under the radical and just put them under one radical. So the derivative of arc sine of x over a is this. And if I distribute that a squared through here, everything gets multiplied by a squared. This is what we get. A squared times 1 is a squared. X squared over a squared times a squared is x squared. So the derivative of arc sine of x over a is this. So the antiderivative of this should be arc sine of x over a plus c. And that's exactly what that rule says. Okay, let's just see that rule in action. See a quick example. Let's say I see 3 over the square root of 81 minus x squared dx. Well, first of all, I notice that it matches that pattern. It matches that pattern right there. I've got a constant squared minus x squared under a radical. I've got a 3 in the numerator instead of a 1, but that's no big deal. We can factor out the 3. So we factor out the 3, and then we've got this. And 81 is our a squared. So a squared is 81. That means a is the square root of 81, which is 9. Now, according to our antiderivative rules, we bring that 3 down, and then we just take the antiderivative of this piece. According to our rules, the antiderivative of this is arc sine of x over a plus c, and a in this case happened to be 9. So we're just matching that pattern. We're saying, hey, that looks exactly like this. Now, if you're saying to yourself, it kind of looks like that, you're right, it kind of does look like that. But over here, I've got the variable squared first minus the constant, and there's an x outside. On this one, I've got a constant minus my variable squared. So that's an arc sine. Okay, so that's that right there. So the derivative of arc sine is this. Now let's verify the arctangent rule. The derivative of it's 1 over a. The derivative of 1 over a arctangent of, having trouble. derivative of 1 over a arctan of x over a plus c is this? Well, first I bring my 1 over a down because that's a constant. And then I'm using the chain rule for the arctangent of x over a. So that's my inside function. The derivative of arctangent of a function is 1 over 1 plus that function squared. My inside function is x over a, and then I multiply by the derivative of the inside, and x over a is the same as 1 over a times x. So this ends up being a 1 over a. So I've got 1 over a times that 1 over a from the chain rule times this, and this fraction squared can be written as x squared over a squared, and I've got an a times a out front, so that's an a squared. So when I distribute that a squared through, look what happens. A squared times 1 is a squared, and a squared times x squared over a squared just gives me x squared. Well, that's the formula. That's the integrand here. So the derivative of this is equal to this, so the antiderivative of this must be that. Okay, so let's see that one in action. Let's say you've got the antiderivative of 5 over x squared plus 4dx. That's very tempting. You might think that's a log, but it's not, because there's an x squared here. And in order for that to be a log, well, I'd have to have a 1 over u du, and the derivative of the x squared isn't up there, so it's not a logarithm. But this does match the form of that arctangent rule. You've got a constant in the numerator, which can be factored out, and then you've got a squared plus x squared, or constant squared plus x squared in the denominator. So that's that arctangent rule. So that 5 you can factor out if you want to. And now it looks exactly like my arctangent rule, except the rule had a squared plus x squared. Clearly we have x squared plus a squared. It doesn't matter because we can add in any order we want, right? So a squared's the constant, that's 4. You take the square root of 4 to get a, that's 2. And then according to our rule, we bring the 5 down. The antiderivative of 1 over x squared plus a squared is 1 over a times arctan of x over a plus c. A is 2. And then you just multiply. That's a 5 over 1. Multiply straight across. You get 5 over 2 arctan of x over 2 plus c. Okay. So we verified that rule and we verified that rule. Let's verify this one. Now I'm going to verify it without the absolute value because taking a derivative involving an absolute value is a little tricky. But yeah, we can think about those special cases, x being positive or negative later. Let's just assume x is positive. Okay, so I want to show that the derivative of 1 over a times arcsecant of x over a plus c is equal to this guy over here. I can bring the 1 over a down. According to my rules for arcsecant, I get 1 over the absolute value of x times the square root of x squared plus, or x squared minus 1, except instead of an x this time, we've got an x over a. Now I've dropped the absolute value. I'm just going to say x is positive, so absolute value of x is the same as x. So this is 1 over a times the derivative of arcsecant, which is this, but I had an inside function, right? So I've got to multiply by the derivative of the inside. It's 1 over a times x. And the derivative of a constant times x is just that constant. The derivative of the plus c is 0. So we end up with 1 over a, and then there's an extra 1 over a, times 1 over x over a, times the square root of x squared over a squared, square the numerator and square the denominator separately, minus 1. These a's reduce. This a I can bring under the radical if I square it and take the square root, and that's legal because a is positive. So I have x, that's just an extra factor, and I can distribute this a squared inside that radical. And if I do, see what we get that integrand. We get this x times the square root of x squared over a squared times a squared. The a squareds cancel and you just get an x squared. And a squared times -1 is a squared. So the derivative of this is this. So the antiderivative of this is this. But it turns out it's actually that with an absolute value on the x. I'm not going to worry about that here. So that is our rule for arcsecant. Now let's actually apply some of these to solve some problems. Actually, I've got some written out over here. Let's look at this first one. It's actually a sum of 3 of those. I notice right away that I've got like 3 of those basically. I've got an a squared minus x squared here, x squared plus a squared here, and an x squared minus a squared here. So those are those 3 rules that we just learned, but they have constants in the numerators. So you want to factor out the constant so that it looks like the form of our rules. So we're going to split this into 3 separate integrals. The constant multiplying us, the integrand here is a 3. You always want to look at the constant in the numerator and the denominator. That's a 3 over 1. So I'll take out the 3, and then I'm left with the antiderivative of 1 over 9 minus x squared dx. Then over here, I want to factor out a constant as well so that it looks like my Arctan rule. My Arctan rule is a 1 over a squared plus x squared. And we can change the order, of course. We can add in any order we want. So the constant here is that 5 over 2. So you factor that out. And we've got that. And then over here, there's a 1 there. The constant here is a 1/6. So I've got a 1 over x times the square root of x squared minus 16. So that's an arcsecant function because of my rules, but that 1/6 needs to come out. A lot of people want to just take a 6 out. You can't. The 6 is in the denominator, so it's a 1 over 6. Okay. Now for each of these, I need to identify a. Here, a squared is 9. So a is the square root of 9, which is 3. Here, a squared is 4. So a is the square root of 4, which is 2. Here, a squared is 16. So a is the square root of 16, which is 4. And we always take the positive square roots with these. Okay, now look at your rules. Notice your arcsine rule did not have a 1 over a out front. The other 2 did. So this is an arcsine because they've got the square root of a squared minus x squared here. So we have 3 times the arcsine of x over a. A is 3. And then here, I bring that negative 5/2 down, and I've got the antiderivative of this. Well, that's an arctan, so I get 1 over a times the arctan of x over a plus c. A is 2. And then over here, I've got a 1/6. That's an arcsecant. You get 1 over a times the arcsecant. The rule has that absolute value in it of the absolute value of x over a plus c. This time our a is 4. So that's our answer. It's just not simplified. I would clean up these coefficients and then you'll be done. Then you'll have an answer that I was going to say my labs, but we're using WebAssign. WebAssign will like. It's also always good to simplify your answers if you can. Okay, so that's that. Now this one looks tricky, and it is a little tricky. But once you figure out how to do it, it's not so bad. Now notice that if it was just that 10 up there, I have a constant over x times the square root of x squared minus a squared. That's an arcsecant. And if that 10 wasn't there, if I had the 2x over that, well, one of the x's would reduce, and I could use a u substitution. But the way it stands right now, I can't do anything because, well, I can't do the u sub because the derivative of x squared minus 9 would be 2x, and I've got a 2x squared minus 10. I can't do anything with that minus 10. It won't work. And it's not an arcsecant because of the 2x squared. So this is what we do. We often do this. We try separating the numerator. And we've done this before in other problems, but most of the time in those problems, the numerator was relatively simple. The principle is exactly the same. We're going to have 2x squared over the denominator. And I'll have that as a separate integral, minus the integral of 10 over that denominator. And this turns out to be an arcsecant function, and this ends up being a u sub problem, but we've got to simplify first. X divided by, or x squared divided by x is going to be 1x. One of those x's will reduce. So this is a 2x over the square root of 2, or x squared minus 9. And I know I can use a u sub for this, because if I let u be that expression under the radical, watch what happens. Du is 2x times dx. Isn't that nice? So you've got exactly what you need right there. So I've got, this integral can be rewritten as 1 over the square root of u, where u is x squared minus 9, and 2x dx is the same as du. And I can bring that up to the numerator. That is a u to the negative 1/2 power. So we add 1 to the exponent, divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2. And then don't forget to back substitute. That 1/2 power is the same as the square root. You replace the u with x squared minus 9. So we had a u sub for this. And then over there on that side, well, that's just an arcsecant. So I think I might factor out the 10 and write it this way. Oops, I guess it's the square root of, that's an x times the square root of x squared minus 9. Here our constant squared is 9. So a is 3. And if you're like, I don't know that that's an arcsecant yet, you still have to learn these rules. Keep referring back to them. Maybe put them on a note card or a sticky note, keep it nearby, and keep referring to it until you don't need to refer to it anymore. We say, okay, well, a must be 3. Then according to our rules, I bring down my negative 10. And the antiderivative of this is 1 over a times the arcsecant of the absolute value of x over a plus c, and a is 3. So we substitute in 3, and then we simplify. So we get 2 times the square root of x squared minus 9 minus 10/3 times the arcsecant of the absolute value of x over 3 plus c. And that's that right there. Okay, so sometimes these rules don't directly apply, but if you simplify, if you break up that numerator, you see two terms and you see if there's a constant there, that constant over this is one of your inverse trig antiderivatives. Go ahead and split it up. Sometimes you'll have something like this that happens. One of those might be your inverse trig function and the other one might be a u sub. That actually happens a lot. Okay, let's look at this. Now on the surface, this does not look like any of those inverse trig rules, but it actually is one of them. It's one of them with a u sub built into it. Now, notice that there's no square root. So the only one that even looks remotely like that is this, because it's the only one without a square root. In order to use this, I would need to have a squared plus u squared, so it's some function of x, squared, and du would also have to be a part of this somehow. So the only way this will work is if I can write that denominator as a squared plus u squared, and we have a du right here. Then we'll get 1 over a arctangent of u over a plus c, and we can back substitute. We just have to figure out what that u is. I'm looking for a function squared, and my hope is that the derivative of that function squared, at least a constant times that derivative, is up here somewhere so I can substitute and finish the problem. I think a big hint is that that numerator is an e to the 3x. And we know this property from algebra. If you have something raised to a power raised to a power, you can multiply those exponents. That also works backwards. So if I see that 6x, I can split that into a 6x times, or a 3x times 2, which means I could make that an e to the 3x squared. Let me show you what I mean. So this is e to the 3x in the numerator. And I'd like to rewrite that e to the 6x as e to the 3x quantity squared. Now, according to this rule, that's e to the 3x times e to the 3x. We add the exponents and we get e to the 6x. Or you can think of it as that rule. It's e to the 3x squared. You multiply the 3x and the 2 and you get the 6x. Okay, so we're here now. And even though it doesn't look like it, this is actually an arctangent function, because this is an a squared plus u squared, and the derivative of e to the 3x has an e to the 3x in it. So I should be able to substitute all of this and write this in terms of u. So let's do that. Let's let u equal e to the 3x. Then du is the derivative of e to the 3x. The derivative of e to some power is e to that power times the derivative of the inside by the chain rule times dx. Now there's not a 3 up there, so let's divide both sides by 3, or multiply by 1/3, same thing. That'll give us that e to the 3x dx by itself. So this ends up being 1/3 of du. And this is a 49 plus u squared in the denominator. So I can rewrite this whole thing as this. So I've got a 1 over 49 plus u squared, and the e to the 3x dx is exactly the same thing as 1/3 du because of that algebra we did, because of the computation we did to get du, and then dividing that 3 out gave us e to the 3x dx equals 1/3 of du. So I'll bring the 1/3 out front, bring the du to the far right, and then this is my rule for arctan. It's exactly like that. The only difference is I've got u's instead of x's. So identify a squared is 49, so a is the square root of 49, which is just 7. And then according to my rules, I bring my constant down, and then I get 1 over a times arctan of u over a plus c. My a was 7. And then I simplify, that's 1 over 21 times arctangent of u over 7 plus c. But we're never done until we get everything in terms of the original variable. Since our original variable was x, we've got to substitute. We replace u with whatever it was in terms of x, and u was 3x, e to the 3x, so that goes right there. So that's our answer. Okay, now this one is a little tricky because it looks like arc sine, doesn't it? Got a 6x minus x squared under that radical, and there's an a squared minus x squared under that radical. Problem is, this one doesn't have an x, it just has an a squared, it's just a constant. And this is a constant times x. So here's a technique that we'll use more when we get to calculus 2. If your expression involves an ax squared plus bx plus c, we can complete the square to rewrite this, and often after completing the square, we can use a u substitution to solve the problem. And that's typically what happens with these inverse trig functions. Okay, so basically what we're doing is we're taking this expression under the radical, oops, lost my pen top, and we're rewriting that as a perfect square plus a constant. So first I'm going to rewrite it in a different order. We usually like to have the x squared term first, so we'll write that down first. And then we remember that we want to have a coefficient of 1 in front of the x squared. So we're going to factor out a -1. -1 times x squared gives me -x squared. -1 times -6x gives me +6x. Okay. Now that I've done that, now that I have a 1 in front of my x squared in those parentheses, the number multiplying x, we're going to call that b. You want to take half of that, that's -3. And then take that number and square it. -3 times -3 is 9. That's what we need to add to complete this square. But be careful, actually let me make those parentheses larger. If we're adding 9 in the parentheses to make that a perfect square, we also have to subtract 9 in the parentheses to compensate for what we just did. Now this is a perfect square, and then we have this extra -9 that was necessary in order to make this result equal to that original result. And this is equal to this, and we want this to be equal to this, which is equal to this, so that we can make our substitution later. That's the whole point, is to be able to take this and rewrite it in a new form that will allow us to substitute and then make a u sub to evaluate the integral. Okay, so we added the 9 to complete the square. And we said if we're going to add 9, that's fine, as long as we also subtract 9. Okay. So now let's simplify. The whole goal was to write this as a perfect square. So I've got a -1 times this perfect square, which factors to x minus 3 quantity squared. And then you've got a -1 out here times that -9. If you distribute, that's a -1 times a -9. That's going to be a +9. So that's 9 minus the quantity x minus 3 squared. That is identical. I know it doesn't look identical, but it is identical. It's the same thing as that. It's the same thing in a different form. And we want it in this form, this more convenient form, because then we'll be able to evaluate the integral. So watch what happens. We're going to replace this expression, that expression that we had before we completed this square, to that equivalent expression that we got after we completed the square. So we've got the integral of 5 over the square root of this. So you're replacing the 6x minus x squared with 9 minus the quantity x minus 3 squared. And watch this. That looks just like our arc-sine rule, except instead of an x squared, we've got a u squared. So that's a squared minus u squared under the radical. So that's probably going to work, provided that we can substitute that dx for a du as well. Everything needs to be written in terms of u, not just this part. Hopefully we can write everything in terms of u, and then we can solve the problem. So let's identify an inside function. Now, a lot of students say, well, all of this is under the radical. Shouldn't that be my inside function? That would work if the derivative of this was up here somewhere. But the derivative of this is actually -2 times the quantity x minus 3, and we don't have an extra x minus 3 out here somewhere. So we don't want that to be our u. Instead, I would choose that as my u. Let's let u equal x minus 3, because then it looks like a squared minus u squared. Then du is the derivative of that times dx. Derivative of x minus 3 is 1. So we have 1 times dx. So du and dx are the same thing. So now our integral can be rewritten this way. That 5 we can pull outside. You still have a 1 in the numerator. And you've got a 9 minus u squared under the radical times du over there. And now that looks like an arc-sine rule. Exactly like that. It's just arc-sine of u over a instead of arc-sine of x over a. So we identify a squared. A squared is 9, so a is the square root of 9. So that's 3. So then we have 5 times the arc-sine. Arc-sine is the only one that doesn't have that 1 over a out front. Times the, or this is arc-sine of u over a plus c. A was 3. And instead of an x, you have a u. Don't forget to back substitute. U was x minus 3. Okay. Now these problems towards the end were more advanced problems. They're the types of problems that we work in Calculus 2 at the beginning of the semester. So these are really previews of what you will do next semester. There are some like this in your homework, but I'm not concerned that you become a master of these. I'm more concerned that you know how to solve problems like this one, and then maybe separating the numerator, problems like this. We'll get to these other ones that involve u substitution and completing the square more next semester. But we are doing u substitution this semester as well. So this is a good opportunity to preview the more advanced problems that you'll see in Calculus 2.